Yeah, my name is Ilona Glatt. I'm a business manager for battery applications and also for the hydrogen applications, which is fuel cells and electrolyzers. All experts, hydrogen experts from the master market, would like to welcome you in this session, of course. Some of them are here in the back, and then we also have Anja here. And some of them can't attend this session because there are parallel sessions, and we have to split up a little bit. But if you have any questions, you can ask any of them, and they will be happy to answer you or to guide you to the right person. Not only through the session, but anytime. I already said I like discussions, and that's actually what this is all about. I mean, it's about you. You are making this event very special, and it's about your applications, your research, which is important to make this event a success. So, and special thanks to the guests who have the furthest to travel from Eastern Asia, from Japan, and also from Korea. So especially thanks to the speakers. We already had these speakers in the plenum session, and they're really, really interesting talks. Maybe we can have a little bit ongoing discussion about the talks later on. So thanks to Kato-san from Toyota, and also thank you to Matsumori-san from Honda, and also, of course, to our partners from Trinity and from STSK, that you always come to our events. Thank you, and of course, to all of you. In the next 2 hours, we have a very interesting program. We start with a welcome, which is already over. And next, I will guide you through some hydrogen energy applications that you can do in GeoDict, or why would you use GeoDict for research in this area. And after that, we will have a talk by our Deputy Head of Development, Sven Linden. And he will give us an update on feature requests which were handed in by clients in the hydrogen business. And he will just tell us what is the status of these requests. Have they been slotted in? Are they working on it actually? What is the plan with this feature? And this will be followed by a discussion. We can already have the discussion during the talks, but if you there's a slot for it, so that there is time for discussion. So that's the important point. And then we have a short break where you can go on with the discussions if you like. After the break, we will have 2 live demonstrations. The first one will be given by Jürgen Becker, who is the head of our support team. And actually, he started in the beginning, well, 15 years ago, something like that, started with the hydrogen applications in GeoDict. So he's kind of the pioneer for this kind of applications. And he comes back to his roots today and give us a live demonstration of how you can calculate relative permeabilities in a compressed PTL. And after that, we will have a live demonstration of a new feature, which is the unresolved mercury intrusion experiment in an MPL and GDL compound, because one is resolved, the other one can't be resolved if you have a reasonable structure size. And there's a live demonstration given by Arne Jakob, who is the deputy head of our projects team, and he will just guide you through how to use that feature. So I will start with the applications in GeoDict for the hydrogen applications. And we've talked a lot about, heard a lot about GeoDict 2025, which is new and out now. And maybe you're asking yourselves, what does that mean for me as a hydrogen researcher? Yeah, I will answer that question, but not only for GeoDict 2025, but also for GeoDict in general. To do so, let me give you an example. One of our clients once said, in the 10 years since we started using GeoDict, the cost of our fuel cells has been reduced by 90%, the weight of our fuel cells has been reduced by 50%, and the performance stayed the same. So what does that mean? If you follow on with an example, just imagine we would be talking about the Mirai. That's just an example. I invented that. And I have some numbers taken from the US Department of Energy from 2016, which is almost 10 years ago. we imagine we have an annual production volume of 50,000 fuel cell stacks, and for this production volume, the MEA assembly, the membrane, GDL, MPL, and catalyst layer together is roughly $12 per kilowatt in production costs. So if you assume that, and you assume also the power of a Mirai fuel of the fuel cells in a Mirai of 128 kilowatt, the production cost for the MEA for one Mirai is roughly $1,500, and the yearly production of the Mirai is 30,000 per year. So with the 90% reduction in production costs, we would save 40.5 million per year. So that's just an example, of course, but to give you an idea, I think it really serves well as a nice example. So why are we here? If we want to decarbonize our industry, electrolyzers as a green hydrogen, as a green source for hydrogen, are really important. They are vital. Hydrogen is needed for several parts in the industry, very important ones. It's needed for oil refining, which is a little bit of an irony, but it's true. You also need it for fertilizer production and for steel production, and also for the cement production. For all of these parts, the hydrogen is needed. And currently, the hydrogen comes, well, currently 2 years ago, almost 3, 99.1% of all the hydrogen produced, even more, is from fossil fuels. So green hydrogen is only 0.1%, while blue and gray hydrogen, so the fossil fuels, is all the rest. And if we want to decarbonize our industry, it's obvious that that can't stay that way. What we do want to have is something like that. That would be nice, right? And if we do so, we don't really need the oil refining in that amount, at least. And we could replace that by fuel cells to ensure the energy grid, so electricity for everyone. So why isn't that the case already? That would be really cool, so why not? Yeah, the answer is very easy and very hard to solve. The gray or blue hydrogen costs much less in production than the green hydrogen. So less than half the price. So what we need to do is to lower the costs, to close that gap between the costs for these two types of hydrogen. And one way to lower the costs would be to improve on the performance. I know that's not the only thing that needs to be improved, but it's one part in the puzzle, improve the performance of the electrolyzers. And the question is not why to improve the performance, but how to improve the performance. What can be done? You can imagine the performance of the electrolyzers, but also for the fuel cells, also true for the fuel cells, is determined by transport processes inside of the MEA assembly. So we have to transport electrons, we have to transport gases, and we also have to transport water. If that's true for the electrolyzer as well as for the fuel cell. And the network for the transportation needs to be well organized. Like in a city, if you haven't it well organized, you will get traffic jams and obstacles, so the transport will not work smoothly. And this is how the performance of the fuel cell can be optimized, by optimizing this kind of pathways in the MEA assembly. And this is where GeoDict can be of use. What you do afterwards to connect the microstructure properties or the transport properties that you determine in the microstructure to the performance is you usually have a 1D performance model, or maybe 2D, but a larger scale. And you need input parameters to run that model. And these input parameters at least partly depend on microstructural properties. And what was done so far is, or often done, is these parameters were roughly guessed sort of educated guess, of course, but in fact, it's more or less guessed. And with GeoDict, you have the opportunity to calculate these properties and connect them to the microstructure. And if you change the microstructure, these properties will change, and thus the performance that you get out of your performance model will also change. And during the next minutes, I would like to show you a few examples that you can use to connect the microstructure and use or calculate the properties of the microstructure, which you can then later on use as input parameters for performance models. The first of these examples would be to calculate the porosity and the pore size distribution of a microporous layer or a catalyst layer. They look very similar for analyzing the porosity or pore sizes. That works the same way. The next point would be to calculate the electrical conductivity of a gas diffusion layer. Yeah, we also have to transport the electrons through the gas diffusion layer to have a driving force for the electrolyzer or for to actually operate a fuel cell. And then the third example is probably the most complicated one, most sophisticated one, is the transport of the gases and at the same time of the water. And here we do have, in this entire session, we do have three examples. One is an example for material design of a GDL, which is here. You can see this icon that should symbolize that we have a real design study here, while the other ones were just for observation. And here we have a design of the material. And then in the last 2 points, I will just motivate the live demos that we have after the break and just explain why would one like to do that. The one was the permeability of the PTL, which is compressed by the bipolar plate. And the second one was the diffusivity of the GDL-MPL compound. I think we don't need that schematic, and we'll skip over that, but just to visualize where are the parts where we are talking about. And there's one thing what we need to have a look at all of these examples. We need to have a structure. We need to have something that we can work on. And what we do here is we have a realistic digital twin of a real material in the digital world. So it's just a copy, so to say, in the digital world of the real material. And how do we get that? Let me show you a little bit how you get a structure into GeoDict, which we then can call a digital twin. So the most straightforward way to get there is you would have a 3D scan. In this case, you can see a micro CT scan of a gas diffusion layer of a fuel cell. And if you scan it, you get gray values from the CT scan, and you can import this into GeoDict, and every gray value will become one material phase. And then you can reconstruct it in 3D, and you have a representation of the real material in the digital world, which you can already call a digital twin. So remember, if you have a digital twin like that, you have an exact representation of your material in the digital world. And in the case of the GDL, the individual fibers are exactly those as they are in the real world. And they have the same location, same thickness, everything same. And the properties on the macro scale are identical to the original material. For example, you would have the same permeability of the material. That would be a digital twin. Then we have a concept of a statistical digital twin, which is very similar, but not the same. With a statistical digital twin, you would have a digital representation of another part of the material. If you look at this image here, you have a carpet, and we have two different patches of this carpet. You would have the fibers in different locations. They would have maybe different thicknesses, the individual fibers, and you But in the statistical sense, you would have the same properties. It would have statistically the same fiber distribution, fiber length distribution, thickness, curliness. So you would end up with the same properties on a macro scale, like, for example, the permeability. So if we want to do material design, which is what GeoDict is really good at, we need the statistical digital twin to be able to alter the material. For example, say we want to have a different fiber length distribution to end up with different properties on the macro scale. As long as we have the same properties on the macro scale, we didn't do any designing, right? So if we want to do designing, we have to alter the material. And this is what we need a statistical digital twin for. In GeoDict, you have several options to create this statistical digital twins or structures in general. For granular structures, we have options, and also for fiber structures, and also for sintered structures, which would be valuable for the SOFC fuel cells especially. And then we have some options to make it a little bit easier to create realistic structures. For example, we do have an agglomerate generator, which creates these kind of agglomerates that you can see on the bottom here, so like these here. And you can use these agglomerates and put them in into a volume and generate a structure which is constructed out of these agglomerates. This is very helpful if you want to create, for example, a catalyst layer, which is done here on in this example, because a catalyst layer consists of this kind of agglomerates. And then you have usually a covering of ionomer, which you can add later on in platinum particles and so on. But this kind of agglomerates gives you the typical pore size distribution that you have in this kind of layer. So you have large pores, you can see, for example, here in the scan, but you also have these smaller pores in between the particles. And it's much easier to achieve if you have these agglomerates to start with. That's another thing that we already heard about in the plenum session, the 2D to 3D app, where you can use 2D scans to get a 3D structure. I was actually impressed by the 3D TEM scans. But if you have TEM only in 2D, that's a different thing, of course. Same for FIB-SEM scans. FIB-SEM scans are very difficult to get, especially for the micropores layer, or even worse, the catalyst layer, because they're very, very small particles and it's mechanically not very stable. So if you want to have a good image of that, I have never seen one, which is actually one of the reasons why we started with the SOFC cells for the 2D to 3D app. Now it's also working for battery structures, and it's also working for fiber structures, but we're still looking for a really good scan of an MPL or catalyst layer. So if you have a really good scan of an MPL or a catalyst layer, you would be very interested to work with you on creating or improving on the 2D to 3D app using that kind of scan. So please let us know. So now we do have a realistic digital twin in the digital world. We can start analyzing that. So let's start with an example of the pore size analysis of the micropores layer or catalyst layer. Here on the left-hand side, you can see in gray the structure of a micropores layer. And on the right-hand side, we have a graph which you also get from experiments of mercury intrusion. So you get the pore size distribution, or the pore sizes. So you get the pore sizes on the x-axis, while on the y-axis you have this rather cryptic measure for the amount of pores that you get for this size. And the exact same graph you get in GeoDict if you run a mercury intrusion experiment. And then you can compare this with the experiment, or the digital experiment with the real experiment, and see, does it fit? If it fits, you're probably fine. And you can go one step further with the simulations, because with the mercury intrusion, you only get the throats of the pores, or the sizes of the throats. And for the transport, it's also important to know how big is the pore inside, so the pore body. And this is something that you can get with GeoDict. also hidden pore, so inside of the material. We had that in the plenum talk earlier. And this is something that you can use GeoDict for. And once you have validated your structure using experiments and digital experiments, you can rely on that and go one step further and use things that are not available in the experiment itself. What you can also do in GeoDict is visualize the pore sizes in 3D. So here you have in 3D in color the size of the pores, and you can just see how big is the pore at that I'm just currently looking at. For example, this pore is in red, so that means I have a very big pore here. Here are very small ones, they are blue color coded. Yeah, so you have two options, either reproducing the experiment or even going one step further. So you've seen the porosity analysis, and now go to the electrical conductivity of the GDL. What you can see here is in gray gas diffusion layer of a fuel cell, and you can calculate the electrical conductivity or the electrical conduction of this structure, and you get, for example, current densities in 3D, and you can see if you have any problematic areas, like for example here in the red ones, or here in 2D you can also analyze it and slice through and see a little bit more in detail where there could be any bottlenecks for transportation. So let's move on to the most difficult task, so to say, the gas diffusivity or permeability of the electrodes, depending on the water saturation or on relative values in any case. We will start with the materials design. So it's a design study which has been done quite a few years ago of a gas diffusion layer. I think it was done by Jürgen Becker, so if I tell something wrong, please correct me. It was, I think in 2009 it was done. There will also be a citation later on. So we have the GDL here, and between the gas channel and on the bottom we do see the microporous layer. And in this study, the assumption was that the water which is generated enters in this compound or in this substrate always from the bottom, from the microporous layer in a liquid state. We've seen earlier on in the plenum that this is not always the case, probably never. But for this study, it was assumed that it is the case. You could also assume different or more complicated ways of how the water enters into that layer. But for this study, it's not the important part, actually. So we'll leave it with that way, and we'll start saturating that layer from the bottom. The idea here is, we can just have a look how that saturates. So we have the water entering from the bottom and saturating the gas diffusion layer until it's more or less completely filled. So the idea behind the study is now to do some microstructural design by punching holes into this gas diffusion layer. And as we have a very hydrophobic structure here, the water will presumably start forming or entering into the big holes which have been punched first. So leaving the smaller pathways open for the gas diffusion or permeability. So let's see how the saturation looks like. So it starts at the same location. And you see, okay, at least qualitatively, that works. We have filled the holes first. The punched holes are filled with water while the rest is still open for the gas transport. Does it also work qualitatively? Well, let's have a look at that. Wait a second. If we look at the graph here, we have on the y-axis. On the y-axis, we have the saturation with water in percent of the two GDLs. And on the x-axis, we have the pressure that is needed to get the gas through the structure. And if I let the video run, we can see that for the perforated GDL in red dashed here, we get a different graph than for the default GDL. And in the typical operation level, it's actually a little bit wider than it's shown here, but more or less. So in the typical operation level, we see that we need less pressure for the gas to go through at the same saturation level than for the non-perforated GDL. So in this study, the structural design, the material design worked out. The water fills the perforation first, and it leaves the smaller pores for the gas transport, allowing for higher permeability at the same saturation. Yeah, we have already seen the plenum talks, so we can refer to that. And this was the real world. I mean, this is a study which is done in a publicly funded project, and you're doing the real research, so for real applications. Now let me show you a little bit what the permeability of a PTL in a compressed bipolar plate is good for. We're talking about electrolyzers now, but it would be also true for fuel cells if you look instead of the PTL at the GDL. So what you do during production is you press the PTL and the gas channel together. And while this is pressed together, the PTL is compressed mechanically. You can see that on the image here. This is the gas channel, or one of the gas channels. And during the production of the electrolyzer, it's pressed into the fiber structure of the PTL. And we do get the compression then in the middle of the gas channel. So here we have less compression than on the outer side. And if we want to go into a performance model on a higher scale, we need to enter a permeability value. And the permeability that we get from the relaxed structure is different than the one that we get from a compressed structure, of course. The trouble is if we measure, or if we image the PTL with a scanner, it's usually in a relaxed state. So if you use this image of the relaxed state and calculate the permeability or the diffusivity of the structure and enter this into the performance models, it will probably not be the value that you have during operation. So if you want to have the value that you need for simulating operation conditions, you need to use the compressed structure. And this is what Jürgen will show after the break, how you can use GeoDict, or in this case ElastiDict, to compress the structure in a realistic way and use it for performance models as an input parameter later on. So the last example I want to talk about is related to the last task in the session here, which is the mercury intrusion curve that you get from the compound of the fibers and the microporous layer. So why would you want to do this? Well, scans of the microporous layer or catalyst layer are very hard to get. Already had this topic. So what you usually do if you want to have a scan of this compound, you scan it together with the GDL. And then it's usually not resolved. So the MPL, is not resolved, or you can't really resolve that. So what you can do in GeoDict now is you assume a porous medium for the microporous layer, the one here on the bottom. So for each voxel, you have pore inside as well as solid material. And you say, okay, my porosity, I know that, can assume that. And then you can calculate the mercury intrusion for this entire compound. And you get then the analysis for this entire structure. You can use that again for going into performance models as an input parameter. All right, so that was what I wanted to show you as an introduction to this session. The most important thing is the microstructure directly influences the performance of the fuel cell or of the electrolyzer. And GeoDict can help you to design that microstructure in a fortunate way. And with that, I would like to thank you for your attention.